Lesson 4 is the second of two introductory lessons on the topic of ratio. There's no new rules for this lesson, but there are a couple of definitions. Make sure you've read about those. And let's begin with this quote from an author, G.K. Chesterton. He's also a Christian, and he lived from 1874 to 1936. And in his book, Orthodoxy, he wrote that proportion cannot be a drift. It is either an accident or a design. And you might be thinking, well, what does this have to do with ratio and a picture of a whale? What's that there for? So what Chesterton is talking about here is when you look at a whale, for example, that's a baby humpback whale there in the photo, the various parts like the head, the mouth, the blowhole, which is right there where it breathes, the eye, these various parts, they have a super complex arrangement of proportions relative to each other. So those proportions make a humpback whale and not something else. That's one way we identify them. And when this whale has babies, its offspring will have features of similar proportion. And that's no accident that that happens. And that particular arrangement of features, that's not going to drift over time from being designed to being something accidental, or vice versa. Proportion is not a drift, and in nature it's always evidence of a designer. And then humans, they're created in God's image, designed to be creative like Him as well. So we make things that have proportional features. We see that in art, we see it in architecture, we see it in engineering, all over the place. That's evidence of a human designer, male or female, created in God's image. Proportion, it's about equal ratios. On this whale, the distance from the blowhole to the eye relative to the eye to the tip of the rostrum, the ratio of those two distances, that should be proportional or equal in another whale to help us identify that as a humpback whale. It's evidence that the whale was designed, that God created it, designed it a certain way. If you're not convinced that proportion is not a drift, it can't just be an accident, then try to redraw this whale on your paper. Just look at that picture and just start trying to draw the rostrum and going down to the tail, the fluke down there, and the big pectoral fin that it has. So if I drew it like that, that's starting to look kind of disproportional, right? I drew that pectoral fin really big compared to the rest of its body. And then if I drew its eye in like that, that's looking more like a flying fish than a whale now, right? So the proportions of things matter, and it's definitely evidence of design and not some accidental thing. So what does all this have to do with Part A, titled Proportion and the Christian Adventure? And I mean, how in the world are we relating mathematics? It's supposed to be a math course. Where is this connection here with Christianity? Well, let's just keep thinking about this a little bit more. This is important. Most math courses, they don't talk about God, but mathematics is a tool for studying God's creation. So it may seem kind of strange that we're talking about God, but really I think it's strange that most mathematics courses don't talk about God, and it makes learning mathematics seem kind of not as meaningful and probably even more difficult to understand. So anyways, look at this in Calculus, a Liberal Art. That's a book by William Priestley. He writes this, that the notion of a proportion and equality of ratios, that's what proportion means, is equal ratios, that manifests itself in mathematics as measurement, in rhetoric as analogy, and in music as harmony. Proportion is, of course, closely tied to beauty in all the classical arts. So proportion is much more than just something in mathematics. So that's important to see, just that integrated approach that we try to do in Shormann mathematics, and see that proportion has to do with mathematics right here, but it also has to do with rhetoric, with music. It's tied to beauty. It's much more than just a mathematical concept. But that's what we'd expect in a world created by God, who is both one and many, and with whom relationship matters, how this thing relates to that. So for Christians, we should seek to explain the obvious differences between things, but we should also see how they relate as well. So something you see in government education a lot of times, in a public school education, is that they train students to only see differences in things like fact and opinion. That's a big thing in government education, is to separate these two things. They treat fact as things that can be tested and proven, and then over here you have opinion. And opinions are just beliefs held by individuals. They're not necessarily true. However, not all facts can be proven, like Euclid's axioms and postulates, which we're going to talk about in Lesson 10. These are the foundation of geometry. We can't prove them. They're called self-evident truths. And it's also reasonable to believe in a fact. I can believe that the normal color for a cardinal is red. I can believe that humpback whales have really big pectoral fins compared to a lot of other whales. So obviously there's differences between facts and opinions, but we should also seek to understand how they relate. And that brings us back to proportion. That idea of proportion that should encourage us to find the real harmony that exists between things like facts and opinions. Proportion also helps us see the inherent design in the world. That helps us make the common sense connection between the Creator and His creation, whether that's God, the creator of the natural world, or man, the creator of a man-made thing like a building. So pray for your friends and relatives who may be in government education systems and they just don't get as good of an understanding of the real world like you're getting here, and how things are different but also related to each other. One thing you can help them do is this final thought here on proportion. And as a human designed in God's image, you're filled with incredible purpose for this world and for eternity. It's important to help other people who may not understand that realize that they have purpose in this world and forever. And the time you spend in this math course or elsewhere, it's going to be a lot more fun for you if you think of it not as a horrible chore to trudge through with a lot of complaining. Don't do that. The biblical way to think of this is as an adventure. James chapter 1 verse 2 and 3 says that when we have something that's difficult for us, a trial, to consider that joy, to be joyful about that. And finally, here quoting Chesterton in his book Orthodoxy, again, he said that man must have just enough faith in himself to have adventures and just enough doubt of himself to enjoy them. So there's a balance there, right? A proportion of having faith in yourself, trusting yourself to go and have an adventure, and doing this math course can be an adventure as well. That can be part of that. But then also just enough doubt of yourself to enjoy it, that you don't already know everything. Or maybe you have that attitude of, what am I ever going to use this for? If that's your attitude, you're not going to enjoy this very much. But if you doubt that thought, if that thought comes to your mind, what am I ever going to use this for? And you doubt that just enough, then you're going to enjoy this course a little bit more. So find that good proportion, that perfect proportion. Seek that out of just enough faith to have an adventure here or elsewhere, and just enough doubt to enjoy it. Let's move on to part B, and here now we'll do some mathematics and word problems and proportion. But before we do word problems, let's review just some basics of working with ratios. This f of a fraction of a whole that we call a equals b, those types of word problems, just little simple ones here. So let's just do some examples here. Example 4.1a, 1/3 of 72 equals what number? So remember you doing that maybe in Algebra 1 where you have f of a, which means f times a equals b, and you can use that formula, it's like a formula there, and just substitute in. So the fraction is 1/3, so we'd say 1/3 of 72. So 1/3 times 72 is equal to Wn. We'll put that in instead of b, we'll say use a descriptive variable, Wn, for what number. So now we're just doing 1/3 times 72, and or 72 divided by 3, you can think of it like that too. That equals 24. So That's what number is equal to, 24. B, 0.2 of what number equals 109? Well, I hope you know 0.2 is a fraction, right? Decimals are a shorthand way of writing fractions. So 0.2 is 2/10, right? Or 1/5, that would reduce to. But we can say 0.2 of, so times what number is or equals 109. So to figure that out, we would divide both sides by 0.2 and we'd get, just do that real quick there, and so that's going to cancel everything on the left, and you could do that on your calculator. That's okay if you want to do that on your calculator. Wn is equal to 109 over 0.2. You should get 545 for that. And think about that. Does that make sense? 0.2 of a bigger number, 2/10 of a bigger number, 545, equals 109. Well, yes, that makes sense. If I had 28 for an answer or something, that would be kind of strange, because I can't have 2/10 of a small number to get a bigger one to get 109. So think about your answer when you're done. Make sure it makes sense to you. And then the last one is a percent. Percent is per 100. Again, that's another shorthand way of writing a fraction, right? So here we're going to find the fraction part, which is in a percent form. So we would say P over 100. That's how we write percents. So if you had 20% and you wanted to write 20% as a fraction, well, that whole symbol, the percent symbol itself, that means per 100. So what you're rewriting that as a fraction is 20 over 100. So the 20 part there, that's the P over here, P over 100. So we'd say P over 100 of 185, so times 185 equals 42.55. So here we'd have to multiply both sides by 100 over 185. Or think about this, 185 over 100, that equals 1.85, right? So we could just rewrite this as P times 1.85 is equal to 42.55. Divide both sides by 1.85 and we'd get P is equal to 42.55 divided by 1.85. So then just get your calculator out, do that division, you should get 23. Okay, so our answer we'd say is 23%. What percent? Well, 23%. 23% of 185 equals 42.55. So now that you're back into working with fractions, we had a little bit of refresher there, and making those connections between fraction, decimal, and percent, all different ways of writing fractions. So let's do some proportion. Proportion is equal ratios, right? And proportion word problems have these 3 basic steps. You can follow these on any problem dealing with proportion, and remember, that's part of mathematics, is you have a general idea, like a set of steps or some kind of formula that you apply in a bunch of different situations. So each new proportion problem, you don't have to do it completely differently. If you think you do, then you're going to make math a whole lot more difficult for yourself. So look at this here. Step 1, set up the proportion. Step 2, cross multiply. Step 3, solve for the unknown, and that's it for almost all proportion problems, no matter what they are. So in part 4a, proportional relationships, we saw those are not just about comparing numbers, numerical quantities. A super important thing to understand is that it reminds us that things can be distinctly different but also related. That different things can be related, that's an attribute of God. And the sooner you're able to see that in mathematics, that's going to make all of math easier for you. So look at this example, 4.2. Let's read it first. The model airplane was a 1/25th scale replica. If the actual airplane was 100 feet long, how long was the model airplane. So one thing we do in word problems is we look for keywords or phrases. Scale, scale model, scale replica. That's an important phrase right there, because that helps us think about, well, these things are proportional to each other. So let's set up a proportion of model to actual. We could have done actual to model. It doesn't matter. We just need to be consistent. So model to actual. And so we could use descriptive variables for that, m over a. And the proportion here, or the scale, is 1 to 25. 1/25. Okay? Now if the actual airplane is 100 feet long, how long is the model? So here we can just say the model over 100, because we've been given the actual. So here's our proportion that we want to use. We have three known values, 1, 25, 100. There's one unknown there, the m. So we just cross multiply now and figure out what m is. So we'd say 1 times 100 is 100, and then 25 times m is just 25m. Now we can divide both sides by 25, and so that cancels there. And you can probably just do that mentally. You know how to do that, and that's how we did 4.1c. We just did that division part mentally there to isolate the variable. But m is 100 over 25 is 4. So this has a length to it, how long, so we're not just going to write 4, we'll write 4 feet. 4 feet long is the model airplane, if the actual is 100 feet long. So step 1, set up the proportion. Step 2, cross multiply. And then step 3, solve for the unknown. There's a huge variety of proportion problems, and we're not going to try to cover every single type here, but enough hopefully that you get the idea and you see keywords that would help you set up a proportion and recognize it as a proportion problem. So look at example 4.3. Let's read it through first. Last year the ratio of business startups to closures was 5 to 3. If 20 businesses started, how many closed? What was the total number of business startups and closures? So we have two questions to answer here. Let's answer the first one. If 20 businesses started, how many closed? So what do we know here? Well, we know the ratio of startups to closures is 5 to 3. So we could say S for startup over C for closure is 5 to 3. And if 20 businesses started, how many closed? So a proportion. We need to set up a proportion. 5 to 3 equals 20 startups over C for closure. We don't know that one, but we have 3 of 4 values there, right? So we have a proportion equation, a proportional relationship set up, and we can solve for the one unknown. So cross multiply. 5 times C is 5C is equal to 3 times 20 is 60. Divide both sides by 5. Hopefully you know in your head 60 over 5 is 12. So closures is equal to 12. So that's one answer right there. Closures is 12. Now what was the total number of business startups and closures? There's a couple of ways we can think about this. If 20 businesses started, 12 closed. So the total is 20 plus 12 is equal to 32. There's another way we can do this, though. We can do it like a proportion. We could do the ratio of startups to total. So here what we would say is 5 startups over total startups and closures. That's going to be 5 plus 3. So 5 startups over 3 closures is 8 total. S over T equals 5 over 8 equals 20 over T. Okay, and we cross multiply just like we did just now previously to get closures, except this time it's going to be 5t is equal to 20 times 8 is 160. Divide both sides by 5, t is 32. Just like we got before. So we got 32 two different ways there. You decide, but you just need to show your work on it. You just need to decide which one you want to do to figure out that second question. If you see another problem like this, you can do startups to total as a proportion, or you could recognize, well, I've got 20 startups, 12 closures, just add them, 32. Let's do another one. The mass of iron varies directly with its volume, and at room temperature 7.87 grams has a volume of 1 milliliter. What is the mass of 20 milliliters of iron? Round that to 1 decimal place. So how do you know this is a proportion? Well, here's a key phrase, varies directly. Okay, so when you see that, that's telling you to set up a proportion that as this increases, that increases. As this decreases, that decreases. So mass to volume. That's actually what density is, right? Mass divided by volume. So mass over volume equals, for iron, 7.87 over 1. What is the mass? So we're trying to find a mass, so we set up a proportion here. What is the mass of 20 milliliters? So we're saying that's equal to m over volume of 20. What is the mass of 20 milliliters? So we have our proportion. Cross multiply. So we'd have m times 1 is just m. This will be easy. Now we just do 7.87 times 20, and we'll just write that down just so we clearly understand what we're doing there with the cross multiplication. And so you can just do that on your calculator, and you should get 157.4 grams. Put the units down there too. So varies directly. That means as one thing increases, the other increases. Is that what happened here? Check your work. Just make sure it makes sense. 1 increased to 20. So 7.87 should increase to 157.4. It did increase. As one thing went up, so did the other. So like we mentioned, this is density. Density is mass per unit volume. It's a difficult concept for some students to grasp, especially if their educational system has trained them to think that one thing does not depend on another, that we always think of things as separated. But this is why God's Word should be the foundation of our studies. His Word reveals to us how one thing most definitely can depend on, how one thing relates to another. Let's do one more. This one's a little bit longer. Just read through it though. In a first-class lever like a seesaw, the force varies inversely with distance from the pivot point or fulcrum. On one side of the seesaw, a force of 10 newtons was applied at a distance of 3 meters from the fulcrum. In order to balance the seesaw, how far from the fulcrum must a 6 Newton force be placed on the other side? Are you noticing a pattern in all of these proportion problems that we've done? All of them have 4 parts to them, and we've been given 3 numbers. There's a 4th number that we need to find. No difference here. And this one, a key phrase is varies inversely right there. That's different than varying directly. So as one thing goes up, the other goes down in this. So listen to this. You may also see the phrase inversely proportional to instead of varies inversely. You might even want to make a note of that. Inversely proportional to. So those mean the same thing. And you should think when you see those phrases like that, think that to solve this I need to set up equal products. So the force and the distance here from a pivot. Force varies inversely, and so what we need to do is set up a product, not a ratio, but a product, equal products here. F, we'll call it F1 D1 is equal to F2 D2. And initial F times distance, force times distance, is equal to a final force times distance. So when we see on one side of the seesaw, a force of 10 newtons was applied at a distance of 3 meters. And so we can see that drawn on this diagram. The fulcrum of the seesaw is just like the pivot point of it. 3 meters away, there's a 10 Newton force going downward there. So we'd say 10 times 3, that equals 6 newtons times question mark. We don't know what that distance is, so that's what we're trying to find, is d2. 6 times d2. So we have 30 is equal to 6 d2. So we can divide both sides by 6 here, or we can just think, well, 6 times 5 is 30, so d2 is equal to 5 m for meters. So there's our answer right there. How far from the fulcrum must a 6 Newton force be placed on the other side to balance it? So directly proportional, those are our normal ratios, and the ratio stays constant. Inversely proportional, the product stays constant, right? We have a constant product of force times distance here of 30. So wrapping up this lesson and just thinking about how one thing relates to another when we're thinking about ratio, thinking about proportion. Consider also the 10 major concepts in Shormann math and how those are related to each other. So for example, setting up proportions like this is also important in algebra, where we're solving for an unknown, and that's we're really doing some basic algebra here anyways, right? Because we're solving for an unknown. And so we can't really talk about ratio without doing some algebra as well. It's going to be important in geometry, you'll see in lesson 10, in measurement as well, you'll see in lesson 16, so lots of other places you'll be talking about proportion. Let's go on to part C now, and rate, the concept of rate. Let's talk about that. So the first thing to notice about the word rate is the similarity to the word ratio. Ratio and rate. So you'll save yourself a lot of confusion if you simply remember that when you see the word rate, just think fraction. Rate is just a specific type of ratio where usually two measurements are compared and one has a time component. So for example, if you drove 60 miles in 1 hour, what would your average speed be if you drove 60 miles in 1 hour? Well, think about it. You would say 60 mi for miles divided by 1 hour. That equals 60 over 1 is just 60. Miles over hour is miles per hour, or we could just say for short mph, 60 mph. 60 this over that. Comparing miles to hour, 60 miles per hour. Rate is normally associated with speed. It can really be for comparing any pair of measurements though. And that is a emphasis here is on that word measurement. We're typically comparing two things that were measured or are capable of being measured. So for example, if you're growing strawberries, decided to sell them for $4.99 a quart, your rate would be your cost per quart. You'd say $4.99 divided by 1 quart. That equals $4.99 per QT for quart. So if you understand ratio, then you can understand rate. And that means you can understand calculus too. And we'll be covering that in lessons 20 through 22. So calculus, it's really just about studying rates. So here's an analogy that you can think of here. Proportion is to equal rates. Remember, that's what proportions are, is equal rates, equal ratios. Proportion is to equal rates what calculus is to changing rates. How do rates change? How does something go from 60 miles per hour to 70 miles per hour? That's what calculus is about, is studying how rates change. Proportion is looking at, is this rate or ratio equal to that one? Let's go ahead and do some examples. Let's look at example 4.6 here. Read this through. Another word problem. If John drove 867 miles in 12 hours, what was his average speed in miles per hour? Round the answer to 1 decimal place. The calculators are okay here. So just as a reminder there, you don't have to do long division on this, because the goal is not to see if you know how to do division or not. The goal is to see if you understand rate. And so what you should be doing is just saying 867 divided by 12. 867 miles divided by 12 hours. Just like we did that example earlier of 60 miles divided by 1 hour. Here we're doing 867 divided by 12. And so you should get, rounded to one decimal place, 72.3 miles per hour. We'll say mph for short there on that. And that's it. That's your answer. Look at this example, a little bit more involved, but just go ahead and read it. Elijah bought 3 pounds of yellowfin tuna for $27.75. At a different store, Elizabeth bought 2 pounds of yellowfin tuna for $18.60. Who got the better deal? So in other words, which one had a cheaper price per pound? That's how we're going to know who got the better deal, is who had the cheaper price per pound. So let's compare the rates. And so let's see what Elijah, his price per pound at the store he went to was. And so that's going to be $27.75 divided by $3 per pound. And so that's $9.25 per pound. Now what about Elizabeth? $18.60 divided by 2 pounds. So what is that in dollars per pound? That's $9.30. So who got the better deal? Who had the lower price per pound on tuna? Well, that would be Elijah. Elijah got the better deal. His price per pound is less by 5 cents a pound. So key phrase in this problem, key sentence really is who got the better deal? We can't really tell by just looking at the prices or just the pounds. You have to compare dollar per pound to figure this out, to see what the better deal is. Okay, well that's all for lesson 4.